Okay.
So nothing of value or
I
nothing
think I will
important.
start because we have it's one more
Book is
minute.
the most valuable thing,
Sure, sure. Or at least what's in the book.
but I have a lot of books. Oh, Julien.
Julien.
Oh, on fait ça
Excellent.
pendant
Très bien.
à 2 heures.
Ok,
À tout à l'heure.
ok.
Boîte des chambres, faire poste de 6 mois dans un petit projet. Une société qui fabrique des autos. Ok, tout à l'heure alors, bonne chance.
Merci.
Okay, good morning, everyone. Welcome to the Warren Lecture Series. Today's speaker is Professor Blaise Bourdin. He's from the Louisiana State University. Blaise is a professor at the Department of Mathematics. He got his degree, PhD, from University of Paris North in 1998. Then he did a postdoc at Caltech. And from 2002, he started his tenure at Louisiana State University, where he started as an assistant professor and eventually became a full professor at the Department of Mathematics. His research interests are in computational mechanics, applied mathematics. A lot of his topics do with damage mechanics, optimal design. And with that, I would like to welcome the speaker and give a podium to him.
Thank you very much, and it's really a pleasure to be here. And as I mentioned before, I was having spent a lot of time in warm Louisiana. I was very worried about coming to Minnesota at that time of the year, and so I've been impressed by the weather package that you were able to secure for me, and I appreciate that. Okay, so what I want to talk about today is a phase field approach. So phase field is really my area of expertise in damage mechanics to reservoir simulation or stimulation. I never know exactly how to write the title. And most of the work here has been supported by NSF and Chevron. And the actual grant work is that of two graduate students, Chukwudi Chukwudozie, who's going to graduate next week, actually on Thursday, hopefully, who was supported by Chevron. And Erwan Tane, who's a French student who just started, also supported by Chevron. He's working back and forth between LSU and the École Polytechnique. So the motivation really would be to be able to do some modeling and numerical simulation of hydraulic fracturing. You know, there's been a lot of talk about hydraulic fracturing in recent years. And basically, whenever you see the glossy paper brochures or the slide decks put together by people in hydraulic fracturing, you always see something like that. So this beautiful picture of a nice horizontal well and these nice networks of parallel cracks that nicely remain within the target area and that are perfectly evenly spaced and of equal length and so on. And it seems that in science you really have an unanswered question and unquestioned answer. And so this idea that you will naturally have these nice networks of parallel crack, to me, falls into the second category, to such an extent that it's often also an assumption that is made in lots of models. So this is just one random example of numerical literature where the rotational symmetry was a de facto hypothesis in the computation, because everything is symmetry, therefore we're going to have a symmetric solution, and everything is going to be nice like that. On the other hand, my experience doing fracture mechanics in situations when you have many cracks that interact with each other, we've highlighted several situations in which the interaction between cracks causes loss of symmetry. And so, to me, this picture has always sounded very idealized and maybe closer to wishful thinking than reality. So, in short, what are we looking? So we're looking at the tightly coupled problem of a hydraulic fracturing, so injecting a fluid into a a well into a porous reservoir. And so what I want is to develop the model. I want to implement it with as few assumptions as possible, and in particular, as few assumptions as to the geometry of the resulting cracks as possible. And what I'd like to use this is to study the interaction between stimulated crack. So schematically, why is this an interesting problem? Because you really have these three tightly coupled components. You have the flow in the reservoir, you have the flow in the fracture, and the intercommunication between these two are what? The pore pressure and the fracture pressure, and the balance law, the leak off, so the migration, the mass balance between the fracture and the reservoir. You have the crack propagation that interface with the reservoir flow, because the pore pressure, of course, affects the crack geometry, but also the strain in the reservoir will have an impact on the reservoir flow. And the crack propagation, of course, interacts with the fracture flow, because the domain in which the flow in the fracture takes place is direct consequence of the propagation, but also the aperture of the crack, which is given by the geomechanics, will have an impact on the effective permeability of the fracture system. So you have these three models that we need to couple in a tight manner. Okay. So before I go into the core of the problem, it's also interesting to look at the scale, time, and space involved, because that's what's going to dictate some of the modeling hypotheses. So bear in mind that I'm a mathematician, so I'm not very good with units. So I had to seek help from colleagues in engineering and industry. So I think I got it right. But so we look at the reservoir, so the scale of the reservoir, or the target of the zone of interest in the reservoir would be maybe a few meters to maybe up to a kilometer. And the permeability, so tight oil is, so that's 10 to the negative 18. I don't remember the correspondence in millidarcy, but I think this is correct, to a more classical reservoir. When I say time scale, what I mean by time scale to me is if you stop any change in the external condition, how long will it take to reach equilibrium? So typically on a classical reservoir, it's going to be a few, maybe of the order of a few days. As far as I understand, in the shell's business, the time to reach back fluid equilibrium could be up to 10 to 50 years. So that would be 100,000 to a billion seconds. And so I'm not going to try to look at multi-phase transport. I'm only going to assume that you have a single phase or a single fluid that is in the reservoir. And so at this time scale at which hydraulic fracturing takes place, it seems to make sense to assume that you have a single phase transient Darcy flow. Now let's look at the geomechanics part, that is just crack propagation and deformation of the reservoir. So there, time to equilibrium, so think of how long it takes an elastic wave to go back and forth, maybe 3 or 4 times throughout your reservoir. That's a good measure of how long it would take to reach equilibrium in a dry rock at least. So with the wave speed involved, that would be of the order maybe 10 to the negative 4 to 10 to the negative 1 second. So again, at the time scale at which hydraulic fracturing takes place, it doesn't seem necessary to account for the inertial effect, so dynamic fracture propagation or elastodynamics. So we're going to assume that you have quasi-static fracture. The cracks involved in this problem, the scale is maybe 1 to 100 meter. The aperture typically is from 1/10 of a millimeter to a millimeter, maybe even less so than the 1/10 of a millimeter. So if you assume that there is a small process zone around the crack, you're still going to have cracks that are very, very elongated. The size of the process zone is going to be very small compared to the size of the reservoir. So it's natural to believe that you're in the small-scale yielding regime, especially if you assume that you're not going to have any type of damage in the rock that is away from the crack tip, no plastic behavior. And of course, this is maybe quite controversial, but this is a very helpful modeling hypothesis that maybe we should keep questioning a bit later. Okay. So on the geomechanics part, we're going to use quasi-static brittle fracture. And then comes the flow in the fracture. So the time scale there, how long does it take to reach back fluid equilibrium inside the fracture system without any change in the aperture, without any change in the surrounding pore pressure. So I think it's the order of a couple of minutes, maybe an hour to a couple of days. So that would be 10^33 to the 10 to the 5 second. Again, so we're going to assume that we can assume stationary flow. So we're not going to try to solve a transient problem into the fracture. And because of the geometric shape of the fracture, so very small aperture compared to the really large length, we're going to assume that we can fit Reynolds and Poisson theory. Okay. So what I'm going to try to do is this. I'm going to first talk about the phase field model of fracture itself, because this is what's going to drive the rest of the model. So we're going to first derive a phase field model of fracture from Griffith theory, extend it to bioporoelasticity. Then we're going to use this phase field representation of a reservoir, and we're going to see how we can use it to build a phase field enabled, there's a missing D, sorry, model to do the fracture and the reservoir flow. We're going to see then how we can couple this as tightly as possible. And I'll go into some numerical simulation, so at least try to do some verification. Again, being a mathematician, validation, that is comparison with experiment, is something that is very difficult to do. I don't have access to this type of data easily. And then I apply that to simulating a network of interacting crack. And we'll see if we can recover some kind of interest in physics and try to explain it too. Okay. So let's first go to a phase field model of fracture. And because I said I'm going to build it from Griffith theory, I'm going to spend just one or two slides. One slide rebuilding Griffith theory, at least the way I understand it. And I know Joe and I had discussions on this slide before. So, well, I'll do my best. So let's look at the canonical simplest setting where you have a 2D problem. You have a single crack that propagates along a known path. You have one crack tip that propagates. So really identifying a crack is the same as identifying the position of the crack tip or identifying the crack length. So L is the unknown. And if, okay. So now, the important quantity in Griffith theory, in my mind, are the total mechanical energy, so elastic energy plus work of the external forces in the equilibrium configuration. Then the fracture energy that is proportional to a crack length. And in order to compute this fracture energy, you need to introduce a material property, the critical energy release rate, GC. And then Griffith's argument is energetic in nature. So an important quantity is to see how the potential or the total mechanical energy evolves when the crack length changes. So you make a small increment of crack. Intuitively, your material becomes more compliant, so it takes less energy to reach the equilibrium configuration. So the derivative of the potential energy with respect to the crack length is expected to be a negative quantity. So we're going to call G equals negative dPdL. And so Griffith's argument, you can summarize it into three principles. The first is a crack growth principle, is that for the range of material that we're interested, at the time scale we're interested, the cracks don't heal. So your crack length has to be an increasing function of time. So L dot is positive. The second principle is stability. And one way to see stability is to say, let's assume that you have a small increment of crack. So then the decrease of elastic energy is going to be proportional to G. That's how we build G. The increase of surface energy is going to be proportional to GC. So if you were in a situation where a small increment of crack leads to releasing more elastic energy than it costs in surface energy, well, why stop? You're going to continue. You're going to continue growing. You're going to release elastic energy. It's going to cost you just a little bit of surface energy. And therefore, if G is greater than GC, you can never be in a stable situation. So stability, the fact that you are at all time in an equilibrium configuration, the quasi-static foundation, mandate that G at all time has to be less than GC. And the first part is energy balance. So it says that when your crack grows, the increase in surface energy has to be exactly offset by the decrease in mechanical energy. So essentially, the total energy in a system is just a sum of mechanical plus surface energy. And so you can write it this way, that G minus GC times L dot is equal to 0. So that's if L dot is non-zero, if your crack grows, it has to do it such a way that G is exactly equal to GC. So that's a long version of the G less or equal than GC that you'll probably see in classical fracture mechanics courses, or that the way it's often summarized. Okay. That said, even originally in Griffith's paper, so Griffith never states this equation. The seminal 1921 paper is very qualitative. But there is a little note in the conclusion that is quite interesting in my mind that was ignored for the most of 70 years. And what Griffith states in the end of this paper is that the theorem of minimum energy, and by that he means the fact that in elastostatic, the equilibrium configuration is the configuration that minimizes the mechanical energy. So he says, this theorem of minimum energy could be extended if account is taken of the increase of surface energy. So if you, in your energy balance, you do not include only the mechanical energy, but mechanical plus surface energy, that which occur during formation of crack. So in Griffith's, well, I cannot say if it's in Griffith's mind, but at least in his writing, he seemed to hint that he sees, or he saw brittle fracture mechanics as an energetic formulation, as a minimization of some energy. And indeed, there are traces of variational model of fracture in the mechanics community throughout the years. Very often, you do a stability analysis by looking at different configuration and seeing which one has the least energy. But to my knowledge, it was never really formalized as in a proper, rigorous model based on energy minimization. However, it seems very simple because if you're familiar with optimization, when you look at these three conditions, these really look like KKT conditions for a constraint minimization problem. So this looks like minimization of P plus GCL under the constraint that L has to be positive. And indeed, if you introduce a total energy, so this is your mechanical energy, so it's a sum of the elastic energy minus and it's computed over the domain minus the crack, because if U is a displacement, the strain is singular along the crack set where the displacement becomes discontinuous. So your total energy is the sum of the mechanical energy in the domain minus the crack plus a worth of external forces plus GC times the crack length. And so one way to see this system of three equations is just as finding a pair displacement and crack length that satisfies the crack growth hypothesis. That satisfies, so I wrote it as unilateral stationarity, that is, that the derivative of this quantity with respect to L is 0, modulo the crack growth hypothesis, and with respect to U is 0. So derivative with respect to U is just static equilibrium for a given crack length. And derivative with respect to L equals 0, at least positive because of the constraint, is just the stability equation and the energy balance, which recovers U this. So this is just a formal mathematical reinterpretation of this system of three equations. Griffiths as growth, stability, energy balance is the same as a series of minimization of this energy with respect to U and L under the constraint that L has to increase with time. Okay. So the next step comes from Gilles Francfort and Jean-Jacques Marigot in France in the mid-90s. And what they suggested is that, in the end, we could make a leap of faith, is to say, instead of assuming that your crack is prescribed and use this in this energetic argument on a given path, which requires that you have another way to find the crack path, what they suggested is that we could actually extend the search scope not only to finding just the length of a crack over a given path, but to finding the crack geometry itself. So if you go back to this energy, so mechanical minus work plus a term that is proportional to the crack length for any displacement and length, what they propose is for any time or loading parameter T, any displacement U and any crack geometry gamma that is compatible, that is kinematically compatible with U, to define an energy that is the sum of the mechanical energy away from the crack, plus or minus the work of the external force, plus this term that is, so Hn minus 1 is just mathematical mumbo jumbo for the aggregate length of gamma in 2D and the aggregate surface of gamma in 3D. So it's essentially the same thing as a Griffith's energy, but it extended to account for any crack geometry instead of just looking at the length of a crack along a known path. And so they postulated an evolution now, saying that we're going to find U and gamma that satisfy exactly the same problem as before, that is the crack growth, unilateral stability, and energy balance. Okay. Or in other words, that we're going to do successive minimization of this total energy for gamma that contains all previous gammas and all U that are kinematically admissible displacement. So again, so the main difference between a classical Griffith theory and a variational theory of fracture is that when we formulate the problem like that, we don't have to make any hypothesis on the crack geometry. We say the crack geometry at a time t is the geometry that minimizes the extended Griffith energy, so that minimize sum of elastic plus surface energy without any additional geometric assumption. The nice part of that is, for instance, it handles changes of topology completely naturally. How do you handle crack nucleation in a variational model? In a completely natural way. You minimize your energy at a time. You minimize your energy with respect to all displacement and all fracture at another time step. If the new crack set has more connected component or more cracks than before, then you had nucleation. How do you handle merging of crack? Simply you look at your optimal geometry at one time step, you look at the optimal geometry at the next time step, and if the crack have merged, you say, do you have handled merging? There is absolutely no requirement for an additional criterion. What's more interesting is that actually through some fairly heavy lifting, mathematical lifting, you can actually show that this problem admits solution. It's a well-posed problem. You can show that it converges to a time continuous formulation. And it took about 10 years for the math community to get to that point. And I think that's very interesting because it shows that modulo 75 years of mathematical development, for the largest of these 75 years, we always assume that Griffith's theory was incomplete, that you really needed Griffith's theory for the crack length plus a branching criterion for the crack path. Essentially, what comes from that is that if you take Griffith's idea, growth, stability, and energy balance, it actually is enough information to compute the crack path. It is a complete theory. You just need a more complex setting for the concept of optimization for this type of energy depending on the function and the curve. Okay. Now, what is a large caveat of that is that I'm a numerics person. Now we want to do some computing on that. So now we have an optimization problem whose unknown are displacement that is discontinuous. So it's never really, really nice in numerics. But we don't even know where the discontinuities are because that's exactly what we're looking for. And if you go in your mind into the panels of numerical methods that deal with discontinuous displacement, extended, generalized, cohesive finite elements, all of these require that you know where the crack is, and then you're good at finding the discontinuity. What seems like very silly, excuse me, but it's actually quite challenging, is that you not only need to know where your crack is, but you need to know how long it is. And not all approximation of the location of a crack will also give you an approximation of the length of the crack. And one way to think of this is what's called the cab driver matrix. In New York, or in any city with a grid plan, if you want to go to 2 points that are not along the grid line, you're going to do that by following this checkerboard pattern. But the length of your path is never the same as the bird fly distance, no matter how small your grid is. So you can approximate the location of your optimal path, but you never approximate the length of your optimal path. So again, the solution of that was independently derived in the math community, in the mechanics community, and the physics community. So being a mathematician, I will present the math version of that. In the math community, Luigi Ambrosio and Vincent Tortorelli in the early 90s were interested in an image processing problem called the Mumford-Shah problem. And the structure is very similar to that of the fracture problem. So I took off the work of the external forces just to make the equation a bit more compact. So here you have your variational fracture energy, sum of mechanical energy plus the surface energy. So what Ambrosio and Tortorelli proposed is to introduce a epsilon, a small regularization parameter, so it has the dimension of a length. To introduce a secondary variable v that will represent in some sense, and I'll try to explain you how in a couple of slides, that represents the cracks. And so they introduced two additional functions, s and capital V. So in some sense, think of v as a function that goes from, that lives between 0 and 1. V equal 1 corresponds to no crack. And transitions from 1 to 0 are where the cracks lie. So think of a diffuse interface version of fracture mechanics. So S is some kind of a stiffness interpolation. When V equal to 0, you want your S to be 0. When V is equal to 1, your S equal to 1, so that in the region when V is equal to 1, this term is exactly the same as that. But if S were close to 0 along a line, it would simulate the effect of not integrating W on the line gamma. And V is, you can think of it as the cost of doing this transition from 1 to 0. And because you want your V field to be a continuous field and not a discontinuous field, we are going to penalize also the gradient of V. And it turns out with the proper scaling, that is V, capital V over epsilon plus epsilon gradient of V, you can actually show rigorously that when you take this energy and you minimize it with respect to U and V, and then you send epsilon to 0, then the U that you get here converges to the U that you would get here. So the displacement in the phase field variable converges to the displacement in the variational fracture problem. But more interestingly is that your V field converges in some sense. That is, the zones where V is not equal to 1 are going to concentrate around where gamma would be. So now we have a proof of that, and we have the beginning of a numerical method that avoids this issue of discontinuous displacement along unknown discontinuity surfaces. What we're going to do, we're going to take this phase field energy and we're going to try to minimize it with respect to any U, any V. The nice part, if you quickly look at the structure of that, is that U is a nice smooth function now. V is a nice smooth function. So you don't have to deal with discontinuity. You don't have to deal with crack tip singularity because there is no crack tip anymore. So you can use your favorite finite element basis, and you can extend this convergence result to a finite difference approximation, a finite element approximation. Okay. So quickly, of course, well, what you do, what you get is you inherit some compatibility condition between mesh size and regularization length. Because we're going to get a diffuse representation of our crack, the mesh size has to be small compared to the diffusion zone. So that leads to very large problems. So you're going to need some parallel computing. In our case, we use MPI and PETC. A nagging problem comes from the fact that this term is not jointly convex in U and V. You can, it's not too bad, but you can show it. And what it means is that if you will try to do a minimization with a Newton-based solver, for instance, your Hessian matrix becomes non-positive. So all your favorite solvers collapse. Actually, Newton's method collapses too. And you could say, well, just forget about it. It's not very important. If it breaks, it breaks. It does break because the physics of the interesting physics always take place when this loss of convexity also arises. So this is not something you can ignore and say, well, it's theorem says we cannot do, but we'll do it anyway. This is really something that's going to cause a problem. So the most classical method for this is to just alternate minimization in the U and V direction, because you can prove that your problems become then convex in the U, convex in the V direction. So it's not a very efficient numerical method in the sense that it doesn't have the quadratic convergence rates of the Newton method, but it's unconditionally stable, and it always converges to at least a critical point. Okay. So what I plotted here would be a 1D version of this problem to give you an idea of what we're going to look at. So that would be the optimal profile, that is the shape that V is going to take after convergence if you were looking at it on a cross-section orthogonal to an existing crack. So if you had a crack centered at x equals 0, your V field, depending on the type of model you use, will always be 1 away from the crack and transition from 1 to 0 and back from 0 to 1 and stay 1 away from the crack. So from this phase field approach, what we're going to get is not exactly the location of the crack, but a blurred representation. We know that there is a crack in this region where you have a transition from 1 to 0. Again, we don't have an explicit representation of the crack. I cannot draw a line and tell you there is a crack, but I can get some kind of a blurred region and tell you the crack is in this blurred region. And I could also focus it, but I would, at the expense of using thinner and thinner mesh to refine and have a better grasp as to where the crack is. Okay, so an example of this, for instance, the 81 phase model, so your dissipation, so this capital V, the dissipation potential is just 1 minus V, the stiffness interpolation is V squared, and here I'm showing 3 examples. To the left is the crack propagation in a drying thin film, so think of thermal coating under a uniform stress, and what you expect is to get a hex pattern and then subdivision. So this is a work that I did with Quaternion. The double torsion test is a wickedly smart way to compute the fracture toughness of a thin sample. You don't need to, the nice part is that you don't need to try the crack location. You can get the toughness just from the sigma epsilon curve. It just has one flaw, is that in the lab it never works. Is that on the paper you have one nice crack that goes straight in the center of the domain, and if you do your experiment, you always see a crack that curves and jumps to the side of the sample. So what we did is try to understand what are what is the crack path sensitive to, whether it's the loading, the geometry, and so on. So this is an example of you see a 3D crack front that moves along an unknown geometry. This one is very hard to read on such small scale, but it's a propagation of thermal crack in a ceramic. So think of a block of heated ceramic that you quench, or you put on the cold surface, and so you have this cold front that propagates. It creates tensile stresses and it creates crack. And so here you're sitting inside your material and you're watching the crack front coming towards you. But you see the potential of this approach to see this very complicated crack pattern and the nucleation of all these crack and the coarsening phenomenon that leads to larger and larger cells coming towards you. Okay. So what we want to do now is apply this formalism to bioporoelasticity system, recover some concept of crack location from the V field, use the V field to formulate the couple flow in the reservoir, flow in the fracture problem, couple them, and then get some science. So we're almost done, technically. So first is how do we do the poroelastic medium? So we're going to assume that we're in a drain poroelastic regime. And then there are lots of discussion as to what should your stiffness interpolation look like, what should your S of V look like. So our approach is to assume that the V, you can think of V in some sense as a damage variable. And the mechanics community very much thinks that actually 1 minus V as some kind of thermodynamic damage variable. So our belief is that we should look at damage taking place at the sub-pore scale. The reason for that is that we would very much like to be able to simulate the fact that you can create a crack just by increasing the pore pressure and essentially destroying or at least causing distributed damage by just increasing the pore pressure in your material. So that means that we want to apply not the V field to the effective stress, but to the Cauchy stress. So that leads to this somewhat unusual form of the dissipation potential. And then the second part is to recover the applied forces. So recover the work of the external forces, or the pressure force here is just the integral of P UN on each side of the crack. So if you just go back to the reference configuration, it's going to be proportional to P times the normal jump of U integrated all along the crack. Yeah, but we don't know where the crack is because all we have is this V field, so there's something challenging here. So the way we do it is doing a little bit of math. You can show that this term, Pu dot grad V, is actually enough to recover the work of the pressure force. And I can try to give you an idea of why it works, because that really drives one of the complexity later. So from this picture, sorry, maybe this one mostly. Come on. Okay, so you see really the V field, its level lines are really parallel to the crite. So the gradient of V is really oriented along the normal to the crite. So the normal direction of the crite is related to the direction of the gradient of V. The location of the crite is also the location where the gradient of V is high. And so if you now look back at this term, U dot grad V, so the dot product is going to give you the normal direction. And grad V, the modulus of grad V is very high next to the crite and then goes to 0. So on each side of the crite, if I integrate U dot grad V, what I get is almost like hitting U with a delta function plus the direction. So it's going to put a very large weight on U on one side of the crite and not much on U when it goes away from the crite. And when epsilon goes to 0, it's just going to give you U on one side of the crite. Do the same thing on the other side. The normal is on the other direction. That now you get negative U. And so in the limit when this regularization parameter goes to 0, U dot grad V really is going to give you the normal jump of U. But it's a purely local. It works on one side of the crite, and it works on the other side of the crite. And as a matter of fact, when, at least in the case where alpha is equal to 0, we can still show the gamma convergence. We cannot show the compactness of minimizer. It looks very technical, but it has a very strong implication. It means that we cannot show that the minimizer of this energy converges to the minimizer of the variational fracture energy. And we'll see why it will really hit us in the next slide or two. In the general case, we don't know how to do the convergence, at least in the math community has not looked at that closely enough. Okay, so I'm going to try to do a little bit of verification. I'm going to apply that to the Snedden problem. And I'm very slow, so okay, the Snedden problem, we're looking at a single crite that is filled with a liquid with no viscosity. We assume that there's no leak-off, there's no pore pressure. So really, the fluid flow is defined by one parameter, that is the pressure. It's a nice problem because you can solve it in closed form, and you can see that if you look at just a line crite in 2D in an infinite medium, if you look at the pressure increment, then you have nothing inside it happens until critical pressure. And at this critical pressure, the problem becomes unstable in the sense of Griffith, that you cannot control the crite tip location. Your crite tip shoots to infinity. So it's not very interesting. If you look at the dual problem that is minimizing respect to the total fluid volume in the fracture, what you get is that until the volume reaches the critical volume that is associated to the critical pressure, nothing happens. And then you have a stable propagation. You can compute the length of the crite and the pressure volume, the pressure of, in the crite through this expression that's well known. And so these are two computations. So this is the crite pressure and the crite length as a function of the injected volume. The dashed line is the closed form solution, the Snedden solution. These series of lines correspond to various values of the regularization length. And what you observe is when the regularization length becomes smaller, you get closer and closer to Snedden's closed form solution. If it becomes small compared to the mesh size, here the mesh is fixed, then you tend to overshoot on your pressure. So at least we have a good way. We know how H and epsilon should relate, and we have good faith that both coincide. So okay, it's an application to two stimulated crite. It's just to show you that indeed we can recover crite path. Indeed we can do merging, at least from the mechanics standpoint with this, this setting. Okay. I'll skip the 3D geometry. Okay, you can apply exactly the same formalism in 3D. You can get interesting fracture pattern. And instead, I'll go to now coupling with the phase field. So, okay. Let's look at the phase flow problem. Really, we have two problems. We have transient Darcy flow in a reservoir, and we have a steady state Reynolds-Poiseuille flow in the fracture. So the problem is driven by the mass balance, Darcy law, the boundary condition that's in the on the boundary of the reservoir. In the fracture, your mass balance, your Poiseuille law, and so the important quantity is the crite aperture, so the normal jump of the displacement. And these two problems are coupled by the continuity of the pressure and of the leak-off of the flow from the reservoir into the fracture. So I think it's fairly classical that one way you can couple these two problems, you can just write them in weak form. You take the proper finite element shape function, and you can get a weak form like that, where you have some equations that are on the reservoir minus the crack, and some equations that are on the crack. And of course, again, because we don't have the crack in the phase field problem, we don't have an explicit representation of gamma, we need to find a way to compute this integral. And so this takes a little bit of work, and you use what we loosely call phase field calculus. This part is easy. So we want to integrate away from the crack. We know that the cracks are the zone where v is not 1, where v goes to 0. So we just multiply it by v squared. So here we're done, and we've recovered our integrals away from the crack. For this, again, you try to see how you can recover surface integral from the shape of v. The v field is something that is not 1 away, near the crack, or the gradient is also concentrated near the crack. So by just hitting this term by the, for instance, modulus of gradient v, or v over epsilon, that would be about the same thing, you would get the integral. You can convert this surface integral into a volume integral. This part, so you need the surface gradient. So the surface gradient, that is, you need to really get the variation along increment, or spatial increment along the crack plane, the crack plane. So again, you can do the same thing by approximating this way. Okay. Now the last problem you have is you need to find to compute this cubic aperture. Okay, so this one we're quite proud of, so that's why I will extend a little bit. Why is it difficult to compute the aperture? Because the aperture is a non-local quantity. So the phase field gives you easily what's on the left of the crack, what's on the right of the crack, but the cube of the aperture is you need at each point to know what's on the left, what's on the right. And the phase field does not give you this information at all. So the trick is to realize that if we know that our aperture were symmetric, that is, the jump to the left is exactly equal to the jump to the right, then it would become a local problem. So the way to do that is just to express u dot n by u dot n minus the average of u dot n. So the curly bracket are the average across a jump, and the square bracket are the jump itself. So now the problem reduces to can we find the average displacement across the average normal displacement across a crack. And as a matter of fact, again, on the paper in theory, you can do it. It's quite easily. All you have to do is to take any line that crosses the crack. It doesn't even have to be perpendicular to the crack, and integrate or compute the average of u dot n along this line. Okay. And okay, so it sounds actually you need a sorry. You would be u dot grad v along this line, not u dot n. And the idea again is on this line, if the crack does not turn too much, grad v is about in this direction, but it's really focusing, concentrated at this point on this direction, this side. Grad v is in this direction, but it's really concentrated at this point. So when I integrate u dot grad v on this red line, I really get the average of u dot v. The problem is that if you get near the crack tip, that completely breaks down. Grad v in this point is in this direction. Here it is in this direction. What you get is not really the jump of the normal displacement, but you get the displacement in this direction minus the displacement in this direction. So you have to find a way to eliminate to identify the crack tip region and to eliminate them. And so we spent quite a while trying to compute these. To identify this problem. And in the end, what we do is simply look at the spatial variation of the gradient along the line. If the average gradient is far from 0, it means that our line is near a crack tip, so you can discard the informations there. Okay. And so now we know how to compute our crack average displacement. If you know how to compute the average displacement, we can know how to compute the aperture, or the cubic aperture. So we know how to completely formulate the couple flow problem in a reservoir and in the fracture without an explicit representation of the fracture, but just using the phase field representation of the fracture. Okay, so a few words on the implementation. For several reasons. We started by looking at how could we do just an iterative coupling of a mechanical solver and a flow solver. And it's a natural thing to do because maybe you have an existing flow solver and what you want to do is just modify it a little bit to make it aware of this phase field and then try to couple your two codes. So that would be the equivalent of the fixed stress coupling. If you're familiar with poroelasticity, it's very common to, if you don't want to do a tight coupling, to do an iterative coupling where you compute the deformation, you get the stress and in the reservoir. You plug that into the flow problem, you solve for the pressure, and you iterate back and forth, and you can show that this converges. So it seems like a very natural idea to do that. And indeed, many groups that try to do phase field coupled modeling use this type of coupling. It has just one caveat, is that it does not work. And the reason is actually, that's why I presented the Snedden problem. Of course it does not work, because we know that if we fix the pressure, even in this really simple problem of the Snedden, the Snedden crack, you compute a fracture pressure, and then you try to compute the equilibrium displacement plus crack. There is no such a thing as the equilibrium plus fractured, the displacement plus fractured equilibrium. So, I mean, formally, if you want to prove convergence of a iterative coupling, you need some kind of a contraction map. You need to show that if you have small change in pressure, it leads to small change in displacement. Small change in displacement leads to small change in fracture, so there is a chance that it converges. Here, this is not the case. Small change in displacement, in pressure, can lead to very large change in displacement plus crack. So there is no way this type of coupling is going to work. Okay. It only works if you don't, for instance, don't compute exactly the displacement and the crack, or you have to do a lot of fudging around. So instead, what we looked at is to go back to the idea of a stress coupling, a fixed stress coupling. So we're going to iterate computing the displacement and the pressure until convergence. That we know it works. It's the classical stress coupling. So we fix the reservoir configuration, we fix the phase field, we iterate U and P until convergence. We know that this problem is well posed. Once we have the fluid and mechanical equilibrium, we use this information to update the phase field, and we iterate this. And this, although we have not been able to formally prove convergence of this scheme, it turns out to be very robust, and we never had a problem of divergence of this pumping problem when at one step your crack becomes very large and then your pressure drops, so you at the next step the crack has to shrink and so on. So this is very robust. Okay. So I'm going to try to do some verification, and for that I want to see where can I apply this formalism. So this is the classical parameter space from Emmanuel. So Emmanuel, you told me that it actually predates 2002, this. So I'm a bit late. So if you look, you define a dimensional toughness and the dimensional leak-off coefficient. So you have this 4 regime. So to the left is when the viscosity dominates the problem. The toughness has essentially no influence on the flow. This is something that is very challenging for us because all the representation of the fracture system comes from the mechanics, comes from solving the Griffith problem. So if you tell me that the Griffith fracture mechanics, the toughness has no impact on the geometry of the reservoir, I don't know how to recover my phase field. So this edge is definitely something we cannot do. The storage-dominated parts, that's the situation where, for instance, the permeability of the reservoir is essentially 0, is quite challenging because we put a lot of work in trying to replace the flow in only the fracture with a flow in the entire reservoir. So in this regime, we actually have a problem where the equations of the fluid are not defined away from in most of the domain. Maybe we could fix that, but you know. So this is more or less the range of what we can simulate. This blue dot is the Snedden problem, the situation where it's both toughness and storage dominated. That's where we have an easy closed form solution. So what we're going to do, we're going to try to see how close we can get to Snedden while still remaining in the red zone. So this is an example of a computation. Here you have the crack, so the phase field representation of the crack, and here you have the pressure representation. So the color map is not very well chosen, but you see that there is a leak off. You see the pressure increasing away from the crack tip. And you see that the crack grows. If you qualitatively compare that to Snedden solution, so unfortunately, well, can't really, because Chuck Woody didn't put the Snedden solution. So you have to trust my word that when the permeability of the reservoir decreases, that is when you go this way, you get closer and closer to the closed form solution of Snedden. And here what we're looking at is the volume in the fracture system as a function of time. And again, when the permeability goes to 0, you see that the leak off decreases, so most of the fluid remain in the fracture system. So you get closer and closer to the total injected volume. Okay, you can do things like a well shut-in. So you inject, you propagate a crack, then you turn off your injection. I think the old people call that a mini frac problem. They use that to measure toughness and permeability at the same time. So at least qualitatively, you see, you get your pressure increase, decrease during the simulation, and as soon as you shut off, it continues decreasing more. Your crack length stops evolving. Your crack stops evolving as soon as you stop injecting. Your crack aperture increases and then start decreasing. This is the pressure, so you see the leak off as a function of time. So at least qualitatively, you seem to be obtaining what we want. Okay, I don't have much time to go through that, but these are, we can look at heterogeneities in the toughness, the permeability of the Young modulus, and we can really see how you can either constrain a crack to remain in between two layers or having it escape your layer. But what we see is interesting is that numerically we observe loss of uniqueness. There are situations where you have two equally energetically equivalent solutions where when you crack would go up and one where your crack would go down. Somehow the code picks one over the other, but they're exactly the same. So the fact that the problem is symmetric does not guarantee that the solution is symmetric. It only guarantees that the set of possible solutions is symmetric, but there may be non-symmetric realization in this symmetric set of solutions. And that brings me quickly to the interacting set of parallel cracks. So what we want to look is a situation when you stimulate many cracks and you see them, and we would like to reproduce this nice brochure that was sold by somebody. And when we do the computation, here is what we got. So when Chuck Woody got that, he was really worried that he had done something absolutely wrong and that his problem, this code was buggy and it would never graduate. And because obviously this is a perfectly symmetric problem, and therefore the solution should be symmetric, but his computation does not lead to that. So what we tried to do that. So first he looked at just two cracks. So he looked at changing the spacing of the crack and changing the reservoir permeability. So when the cracks are very far away, they don't interface, they don't interact, and they're nice and straight. But as soon as they start interacting, what you see is that either only one of them grows, or instead of having this nice pattern of these two parabolic cracks that go away from each other to minimize the effect of stress shadowing, we would see these non-symmetric patterns. Okay, this is an example. And clearly here the cracks see each other through the leak off, or if they're very close, they see each other through the stress shadowing. So we went back to the Snedden problem and we tried to see, well, is there something really deep in there, or is it just happenstance, or is it just that your program is incorrect? So another student, Erwan, looked back at the Snedden problem. So no leak off. The only interaction is through stress shadowing. So you look at two parallel cracks, and you vary the ratio of spacing over crack length, and we try to solve that. And so what it did is, you don't have a closed form solution as soon as your cracks see each other. The only closed form solution that you have is when they're infinitely far from each other. So instead, it did computation with the full domain, and then using only symmetry with respect to the B axis, the vertical axis, so that would be two cracks that propagates in parallel, or symmetry with respect to the A and the B axis, that would be the fourfold symmetry. Okay. And this, I really like his way to represent. So what he did is he labels the crack tip, and he plots the crack tip location at the end of the simulation as a function of, this is the crack length. So you start with 4 cracks that are close to the origin, and then you stimulate. And so the red box corresponds to the twofold symmetry. So all crack tips are the same length. And the blue situation is the situation when you have not applied any symmetry of your domain. So what he sees is that only one of the 4 crite tip has grown. For some reason, it's crite tip 1. And then he compares the energy of all these solutions. And it turns out that the energy that corresponds to a completely non-symmetric solution is actually much lesser than the energy of these 4 crite tip. So the situation that corresponds to 4 tip is a critical point of the Griffith energy. It does satisfy stationarity and so on. But in terms of bifurcation theory, in terms of energetically, it's actually much more expensive to grow 4 crite tips than just to pick one randomly and to grow it and avoid all stress shadowing effect. So that's we can see it even simply on this tiny Snedden example. If you take if your crites are farther away, so delta over L equals 10, what we get is that energetically the more interesting is still a non-symmetric solution, but it corresponds to growing 3 and 4. So it means that it's more interesting to grow one crite at the expense of the other. So notice that in this setting, what we cannot do is to compute the energy of the anti-symmetric solution. But at least what we can show is that there is a non-symmetric solution that is energetically better than the symmetric solution. So the reason for this loss of symmetry, sometimes you hear people in the industry saying that there has to be some heterogeneity or some difference in the internal original crite, or maybe friction at the injection point and so on. Even all things equal, what we see from this really simple computation is that even in a perfectly ideal situation where all things are equal, you will still get lots of symmetry when you look at 2 crite propagating that are close to each other. Okay, so I'll finish by just say so. What I was able to do is to build a phase field enable fracture solver. So the important thing to remember is you need to do a modified stress iterative coupling. You need to do some work to compute the crite aperture and to make sure that your computation is valid all the way to the crite tip. That loss of symmetry is not necessarily induced by material heterogeneities or boundary or injection heterogeneity or whatever, but it's actually a deep fundamental problem for interacting cracks. And acknowledge collaborators. So Kita Yoshioka is at Chevron, who's sponsoring this project. Chuck Woody, as I said, will defend his PhD on Thursday, and he's looking for a postdoc. So if you need a smart student, I highly recommend Chuck Woody. Erwan will take a bit longer, and Mayank is co-advising Chuck Woody's thesis. All right, I'll stop here.
Thank you for good presentation showing
Thank you.
coupling of strong mathematics with real applications in your life. And my question about Ambrosio approximation, could you show this slide?
Sure.
There is small parameter that you mentioned, V. And small compared with what scale? Because below this V change from
Actually, let me show you the next slide is actually the one with the answer to the question.
epsilon.
Yeah.
Yes.
Yeah, epsilon. Yeah.
I'm sorry. Epsilon change from 0 to 1. Is this small?
No, okay, no. V is the phase field function goes between 0 and 1. Epsilon is the epsilon. This length is proportional to epsilon. So small can take many meanings. So the mathematical community is not interested at what happened for a given epsilon. All they show is the limit when epsilon goes to 0. Now, there's been a lot of work in the mechanics community to understand what these models mean when epsilon is a given parameter. And what we see, and I didn't have time to go through that, is really these type of models behave like a dual criterion fracture model. So the nucleation is driven by k equals k1, k1 equals k1c, for instance, if you have a singularity. So it's always Griffiths, no matter what the value of epsilon is. But if you look at the problem without singularity, you can still nucleate a crack, And the critical stress at which you nucleate your crack depends on epsilon. And we have an explicit formula. So small from the math community means when epsilon becomes arbitrarily small, we converge to a Griffith model. Small from the mechanics community means that epsilon in some sense is related to the defect size in your material and is related to the yield stress in your material. So there is actually a way to estimate epsilon. And we have to do that if we want to nail enucleation away from singularities properly.
My second question is about, you said that you cannot recognize, indicate exact crack line, right?
Yes.
Due to diffusivity of...
Yes.
But you have computational possibilities, and what about grid refinement? You can show this more exactly?
Absolutely. No, you could now refine your grid and you could do adaptive mesh refinement and so on. For some pretty bad reason is the fact that originally we were trying to couple two other codes. The implementation is really strongly limited to a Cartesian grid. We cannot, in the implementation, it's a proof of concept implementation. We don't have the ability to do the mesh refinement. But conceptually, there's nothing that prevents you from doing it, absolutely, yeah.
And maybe one more question.
Thank you for a very nice presentation. I have a question about this epsilon.
Yes.
When you simulate the interaction with cracks, I guess this the epsilon will influence how the crack interact, because this epsilon seems defines the length of diffused distance of the damage.
That's right.
So if you have a few experiments, so that means I guess you have a fixed value of epsilon in your simulation.
So if you have what?
I mean, if you have experiments showing the spacing of interaction cracks, that means that you should have a fixed value of epsilon. Is that right?
Well, so it means that, for instance, in the experiments, when we look at far away interacting cracks, where are these? So for instance, here we really make sure that the spacing of the crack is large compared to the value of epsilon. So what we can show is that as long as this, so epsilon is essentially the thickness of this zone. As long as the thickness of this zone is small compared to any pattern in the domain, you know, if you that it's small compared to the spacing of the crack from the edges of the domain, or the spacing of the crack themselves, or in a very elongated domain, the value of epsilon has essentially no impact on the propagation in the Griffith mode. We can show that on this crack, we really satisfy K1 equal K1C globally, no matter what epsilon is, as long as epsilon is not of the order of the size of the domain or some patterns in the domain. So you do have a lot of freedom in the choice of epsilon.
How about if I want to simulate the spacing of the crack, which is not given to you?
Initial crack or when they grow?
No, it's from the medium that I want to simulate the spacing of the crack, which may be comparable to epsilon, or may not be larger than epsilon. In that case, how big the influence of epsilon is in the results?
Well, this is exactly what we did for the thermal cracks. This is precisely what we did here. So in this, we really wanted to get the spacing of the crack. And what we did is that we match epsilon with the yield stress for this material. We computed, we did a 3D bend, well, we did. We look at the data from 3-point bending experiments. We estimated the yield stress, or the yield stress. From that, we computed the epsilon. We plugged the epsilon into this 3D computation. We found the crack pattern, and I don't show it here, but we were able to do quantitative comparison between crack spacing and numerical simulation for this problem, and we really nailed the answer over 4 orders of magnitude of the crack length.
Right, thanks.
I'm afraid we have to stop here, but we have reception at 4:30 in the faculty lunchroom, and if you have more questions, you are welcome to join the speaker. And let's thank Blaise again.
Thank you very much.